Hi, my name is aaguirre from the Computer Institute of the University of the Republic of Uruguay, and I will present the work Imitation for Motor Learning on Humanoid Robots, which is part of my master thesis, where my supervisors are Gonzalo Tejera and Javier Valucian. Motor control in humanoid robots is a challenging task due to the high number of degrees of freedom that must be dealt with. Most solutions presented for the motion control area rely heavily on domain-specific information about the robot or the concrete motor task to be developed. The motivation for our work is based in finding answers to the question of how to program a motor skill for a humanoid robot with an easy-to-scale and model-free approach. Imitation is an important learning mechanism. We can find it in almost all biological systems, especially among us, human beings. The key concept of learning by imitation and robotics includes the master, typical human, which is expert regarding to the execution of the motor behavior to be learned. A robot trainee who doesn't know how to perform the behavior is the destinatary of the learning process. The trainee does not care anymore about every feasible solution. Rather, he just tries the ones which are both closer to the demonstration and fit well with its capabilities, which improves the learning process, reducing the exploration space. Also, as robots move into a human environment, the ability to learn and imitate humans' behavior based only on observation will become of utmost importance. The learning by demonstration dataset is composed of state action pairs recorded during the master performance of the behavior to be learned. These states and actions must be usable by the trainee. We base our work in a real proposal where the correspondence between the master and the trainee is solved by the means of two functions: the record mapping function, G sub R, and the embodiment mapping function, G sub E. The first mapping defines how the states named with zeta and actions named with A, achieved and executed respectively by the master during demonstration, are recorded within a dataset. On the other hand, embodiment mapping refers to how the recorded state action pairs are finally mapped to the trainee. According to either the absence or presence of the record and embodiment mapping functions, the correspondence between master and trainee may be classified as teleoperation, sensors on the master or teacher, external observation, or shadowing. Concerning to the embodiment mapping function, the authors consider two different cases. When the embodiment mapping function is the identity function and no mapping is present because the demonstration is actually performed on the robot or on a physical identical platform, they name it demonstration case. On the contrary, when the embodiment mapping function is present, there are differences between the master and the trainee bodies, also known as correspondence problems. They call it imitation case, and it will be the case which is part of our study. Our proposal consists in a model-free architecture for the learning of motor tasks in humanoid robots. We base it on the formulation of the correspondence problems as an optimization problem. It was validated in a physics simulation environment using one of the most important and challenging behaviors needed for humanoid robots to obtain a stable, human-like gait. In this picture, we will show the solution proposed, where the biped walk is used as the motion task to be learned. A learning by demonstration multi-instructor approach has been used with the aim of generating diversity, allowing the trainee to reduce the solution search space. For this work, we use the Carnegie Mellon University Motion Capture Database, where sensors on the master have been used as the technique for achieving the correspondence between master and trainee. This technique implies that sensors are placed directly on the master bodies in order to precisely record the demonstration. The record mapping corresponds to the identity function. Using this motion capture information obtained from the master execution, the master performance are represented as vectors where each element represents a pose. A pose is represented as a R63 vector of three-dimensional Cartesian coordinate system for markers position in space. Poses are transformed from the Cartesian space to the robot shown in space. The robot has 18 motors, so the new vector's coordinate belongs to R18. These vectors are used as the initial population for the genetic algorithm, where crossover, mutation, individual evaluation, selection, and generation of a new population is repeated until a stop criteria is reached. With this procedure, we solve the correspondence problems, means by the function G sub E, the embodiment function, obtaining a stable gait on the simulation environment. As it was described, a demonstration dataset is composed of state action pairs recorded during the master performance. The set of states is represented by a set of integer numbers. There will be one state for each measure of the postural position of the master. The set of actions is conformed of the captured position of a set of 63 markers which describe the postural position of the master represented by the vector. The embodiment mapping function describes how the recorded state action pairs are finally mapped onto the trainee. Given a state and the associated action for the master, the embodiment function calculates a new pose for the robot. Each element of the trainee posture, the new pose generated, corresponds to the angular value of each joint for the instant of time t for the motor tasks performed. The information about a motor task, the action and its associated instant of time can be represented using a time series. So the embodiment mapping function can be expressed using a time series of poses as input. Instead of using the previous notation, we can replace the two inputs by the time series. Using this notation, the embodiment mapping function can be seen as the one that transforms the X time series in the Y time series, where Y elements describe the transformed posture that successfully represent the motor task under consideration executed by the trainee. We propose to apply an optimization method to find Y starting from X and using a metric for evaluation of the intermediate calculated temporal series. For the proposed genetic algorithm, the initial population is conformed of the recorded master performance. Individuals are represented by a variable size time series where each gene corresponds with a pose. A specific mutation, selection, and crossover operators are defined. For the case of the fitness function, the fitness function depends on the motor task to be learned. For the biped walk problem, we define as fitness function a weighted sum of attributes that measure the quality of the march. This one was which were used. The proposed crossover operator is a variant of the single point crossover. To ensure a smooth transition among the poses, a cubic interpolation spline is applied in the proximity of the crossover point for the two generated offsprings. Given two parents, the orange and the green, random gene is selected in the orange parent. Then a gene is selected in the green parent where the Euclidean distance between is minimal. to find the more similar pose. A Gaussian mutator is used to explore new solutions that are close to the randomly selected pose. For the pose, some of the joints will be changed after mutation. Near internal pose are recalculated to get a smooth transition using a cubic spline. We can see in the picture, we have the original point. The original point is mutated to this value. So we choose 2 points in time at a fixed length, and using a cubic spline, we recalculate the intermediate points to ensure a smooth transition between poses. The selection operator is an aaguirre operator. We use elite teams and tournament selection. In this figure, we can see the fitness evolution comparison over generation, with and without our imitation approach. Each zone is delimited by the maximum and the minimum fitness through generations. Imitation learning approach, in green, reduce the search space obtaining feasible solutions before the 35th generation in the average case. The baseline, which is in blue, using a traditional random initial population, fails obtaining a feasible solution, as you can see in the picture, where the fitness doesn't improve. Empirical results show that the learning by demonstration multi-instruction approach shows benefits compared with a single master approach. Here we can see the result of applying the proposed method for solving the correspondence problem. Conclusions. The proposed approach allows a human or robot to learn how to walk solely based on human motion capture information without needing a model of the robot. The imitation learning approach has shown a big impact finding a feasible solutions, reducing the exploration space. The use of genetic algorithm technique is an explored but promising approach for the correspondence problem solution. For future work, we are working on solving the reality gap in order to test the obtained results in a physical platform. A similar approach to the one presented in this work for solving the gap between human master and the robot trainee could be employed to solve the gap between the simulated trainee and the physical one. Well, thanks for your time, and please, you can send your question or comment to the email address on the screen. Thank you.